Compound statement is called a tautology if it is true for all possible combinations of truth values of the component statements that comprise S. For example, P or not P is a tautology. Why is that? Because if we construct the truth table, we have P or not P. This is or, so this will be true. This is true. One of these two will always be true, so therefore P or not P is always true. So regardless of the truth values of its component P, this statement is always true. Let's look at this example. Let us check that the compound statement not Q or P implies Q is a tautology. We will be needing the components P, Q, and then we need not Q. We need P implies Q. And lastly, our statement. For P implies Q, this is only false when you have true premise but false conclusion. And then we are going to look at the columns for not Q and the column P implies Q, we have or. For this one, this is true. Not Q is true here. P implies Q is true here. And here, both of them are true. So correct. This is a tautology. If we take P to be the statement that 3 is odd and Q is the statement 57 is prime, we've seen that not Q or P implies Q is a tautology. So this means that in sentence form, we have that. Hence, not Q, so that's 57 is not prime, or P implies Q, so we have 57 is prime if 3 is odd. Recall that if you just have the word if, this is the premise, so we are correct. Here is the definition of a contradiction. A compound statement is a contradiction if it is always false, regardless of the truth values of its components. So take note that a tautology is always true, whereas for a contradiction, it is always false. So for example, P and not P is a contradiction. Here, if we construct the truth table for P and not P, they will never be both true. So therefore, this is always false. Take note that if a compound statement is a tautology, then its negation is a contradiction. Let us consider this compound statement and let us check that this is a contradiction. We need the columns for P, Q, P and Q, and then the column for not P. And then we have Q implies not P, and then the conjunction of these two. For Q implies not P, our premise is Q and our conclusion is not P. An implication is false only when the premise is true, but the conclusion is false. So it happens here. And then for the rest, we no longer have TF. So this is always true. Next, we now consider the column Q implies not P and Q. So take note that it can never happen that both of them are true. Since this is and, it is always false. Now that we have discussed tautologies and contradictions, we are now ready to define logically equivalent statements. Two compound statements are logically equivalent if they have the same truth value regardless of the truth values of the components. If they are logically equivalent, we write it as this one. R is equivalent to the statement S. From the definition, it says that if R and S are logically equivalent, they always have the same truth value. So if R is true, S is also true. If R is F, then S is also false. They always have the same truth values. And that means that if we consider the statement R, if and only if S, recall that a biconditional is true whenever the two statements have the same truth value. So therefore, this is always true. Hence, we can say that two statements are logically equivalent whenever the biconditional is a tautology. Let us show that P implies Q and not P or Q are logically equivalent. We need the column for not P or Q. For not P or Q, this is true here because Q is true, false here, true here, and true here. What about the column? We need the column P implies Q. For P implies Q, it will only be false here when the premise is true but the conclusion is false. So if you now take a look at these two columns, they always have the same truth values, correct? So if I just denote this by star, let's denote this by heart. If you add another column, since they always have the same truth values, this column is always true. I just wanted to show you this to show this remark over here. When you're showing that two statements are logically equivalent, you just have to show that their columns in the truth table will always be the same. They should always have the same truth values. We will be using the fact that not P or Q is equivalent to P implies Q, so hence we write it as a theorem. So remember, P implies Q is logically equivalent to negate the premise, turn the conditional into an or, and then the statement Q. So for example, if I have the statement, if it rains, then the road is wet, it is logically equivalent to the statement not P. What is our P here? Our premise here is it rains. So therefore, it did not rain, or the road is wet. These two statements are just the same. Let us consider other logically equivalent statements. Suppose that we have three statements, P, Q, and R. We have the commutative laws. Disjunction is commutative. The order does not matter. That is also true for conjunction. We have the associative law. So it's like the operations addition and multiplication. If you just have one operation, if all of them are just or, it doesn't really matter where you put the parenthesis. So therefore, we just write this as P or Q or R. We can drop the parenthesis because either way, we will always obtain the same statement. Similarly, that is true for the conjunction. We also have our distributive laws. So take note that you have two different operations here. One is conjunction and one is for disjunction. We can view this as if we have multiplication and addition. Next, we have De Morgan's law. De Morgan's law is very useful because it tells us how to negate a disjunction and a conjunction. How do we negate a disjunction? You distribute the negation, so it becomes not P and not Q. However, you change the or to and. So similarly, if this is and, this becomes or. So remember, do not forget to switch the operation. I will leave it as an exercise for you to verify that De Morgan's law is true. Let us consider this statement. To qualify for President of the Philippines, you must be a natural born citizen and you should be at least 40 years old. Of course, there are many other conditions that you need to satisfy before you can run for presidency. However, let's just consider these two statements. So therefore, what is now the negation of this statement? You will not qualify when, let us negate this, you are not a natural born citizen. And then do not forget and becomes or. For the second one, you negate at least 40 years old. At least 40 years old means you are greater than or equal to 40. Therefore, the negation of that is your age is less than 40. That is the negation of this statement. Take note, this is or. So therefore, if you just satisfy at least one of this, automatically you will be disqualified. Let us find the negation of the following statements. Roses are red and violets are blue. These are connected by the word and. I will no longer write them as PQ. I just want you to negate them automatically as long as you can see the form. These are your components. So therefore, negate this. Roses are not red. Negation of violets are blue. Violets are not blue. And then change and to or. Next, the function f is increasing and concave upward. So when you negate and becomes or and then negate the two components. F is not increasing or not concave upward. Next, number 3. Either Miss Scarlett is not guilty or the crime did not take place in the ballroom. This is a disjunction connected by the word or, and here are your two components. Miss Scarlett is not guilty and the other component is the crime did not take place in the ballroom. So therefore, the negation of this statement is that Miss Scarlett is guilty or becomes and here the crime took place in the ballroom. Last example, line L1 has slope 3/5 or line L2 does not have slope -4. This is a disjunction. So the disjunction becomes and again, let us just get the negation of these two statements. So line L1 does not have slope of 3/5 and L2 has a slope of -4. I will leave it up as an exercise for you to verify that the following are equivalent. P if and only if Q is logically equivalent to P implies Q and Q implies P. This symbol makes sense because it's saying that the direction is both ways. Moreover, we have P implies Q is logically equivalent to not Q implies not P. What is this statement? This is your contrapositive. So it's saying that an implication is logically equivalent to its contrapositive. So remember that. However, take note that an implication is not equivalent to its converse. For example, let us consider the implication if it rains, the road is wet. Its converse is if the road is wet, then it rained. This implication here is true. If it rains, definitely the road will be wet. However, is it true that if the road is wet, automatically, can you conclude that it rained? No, it doesn't follow because it's possible that there is just a leak somewhere. So that's why when you see that the road is wet, you still ask yourselves, right? Did it rain? You do not automatically conclude that it rained if the road is wet. Let us consider another one. If a person is the president of the Philippines, then he is a Filipino. This statement here is true. However, what is its converse? The converse is if a person is a Filipino, then he is the president of the Philippines. Definitely, this is false. The implication is true, but its converse is false. This is an illustration to show you that an implication is not equivalent to its converse. So do not make that mistake. We have already seen the negation of a conjunction. This is equivalent to not P or not Q, the negation of a disjunction. This is equivalent to not P and not Q. What is the negation of a statement? Of course, that is just the statement itself. It is only natural for us to ask ourselves, what is the negation of an implication? It turns out that the negation of an implication is the statement P and not Q. Let us show this without using truth tables. Let us recall that P implies Q is logically equivalent. I am using this notation. It is logically equivalent to the statement not P or Q. So therefore, if I now get the negation of P implies Q, that will just be the same as getting the negation of this entire thing. So it's the negation of P or Q. However, we already know the negation of a disjunction. We get the negation of the components. So that's P and the negation of Q. It will be not Q. And then change or to and. So we get what we want. The negation of an implication is P and not Q. What is this saying? How do you negate an implication? To negate an implication, you simply copy the premise, and then you negate the conclusion, and then you join them by and. So for example, what is the negation of the statement? If you get a 1 in this course, then I will give you 100 pesos GCash. This is just an example. This is not true, all right? So anyway, what is now the negation of that statement? The negation is copy the premise. The premise is you get a 1 in Math 108. And then the conditional becomes and then you negate the conclusion. Let us have another example. If you get an average of at least 93 in your tests and homework, take note, you have the word and, then you are exempted in taking the final exam. So I will turn this into simple parts. So we have grade of at least 93 in tests and grade of at least 93 in homework. This is your premise. Then you are exempted. That is the propositional form of this statement. What is now the negation of this statement? Let us recall that the negation of an implication is copy the premise, change implication to end, and then negate the conclusion. So therefore, it's copy this one. We have the conjunction and then negate the conclusion. You are not exempted in taking the final exam.